on this panel, the ozone is plotted on the y-axis and solar radiation on the x-axis. Whereas in this panel, ozone's on the y-axis and wind speed on the x-axis. And in this panel, ozone on the y-axis and temperature on the x-axis. And similarly for all the other ones. And then at the bottom half, it reverses them all, it plots them around the other way. So it's a bit of redundancy there. And you can do things with that. But you have to stare longer, because there are more variables, basically, and see what's there. But you can see things. This is quite a strange plot here, because there's not much scatter for ozone when solar radiation is low, but a lot of scatter when solar radiation is high. So you're already seeing things that we didn't know before. There's a negative relationship here between wind speed. When wind speed is high, ozone is low. Wind speed is low, ozone is high. And so like that. There's quite a nice relationship between wind speed and temperature there. Which you hear the weather forecast talking about the chill factor and so on. And when wind speed is high, temperature low, and so on. So you can look at all those. I've got another one here. You can do more things with these. These are almost default plots now, these ones. This is a histogram, histograms of the individual variables in each panel, if you want to. And I've drawn here what's called a low S line. I was going to talk a little bit about low S, but it's a locally weighted scatter plot smoother. It's a standard command in R, and it's quite useful for helping you to see patterns in scatter plots with lots of points in them. And you see this one here, it's more or less a linear relationship. The lowest line, there's no function line imposed on it, it's just a locally weighted smooth. And these are a bit strange. That's anyway, it's showing you those. What else do we want to talk about? What's the time scale here? Do you want me to? I might show you a couple of co-plots, and then you can ask questions about things. Here's a co-plot of the ozone against temperature for each month. So I've started up a bit from the default one in R, but it's essentially that. So the temperature on the x-axis in each little panel is a month. The ozone's on the y-axis. So I've got 5 scatter plots, but they're plotted in sequence like this. And so co-plot means conditional. It means I'm plotting ozone against temperature conditional on months. It means for each month. If you're interested in the language of random variables, it's ozone against temperature given month. And so you see, what can you see there? You can see little patterns. In each panel there's a sort of increase, a positive relationship, but they're different per month. So it's a rather slower slope in June when the ozone is low, the temperature's varying with fewer points there. This has got a slight extreme value there. This is a rather high slope, but of course the points are fewer here, and so it's harder to see patterns because you don't be fooled by seeing a straight line between 5 or 6 points. But nevertheless, you can stare at that and see whether you can see anything useful. I've done another one with co-plot with 2 variables here. This is another one. So I've got my 4 variables all together on this graph, but 2 of them I've categorized. So I've got wind. I've taken all the low values of wind, lower than some fixed point. So low windy days and not very windy days. Same with solar radiation, low and high. And for each of those 4 combinations of wind and solar radiation, I've plotted a graph of ozone against temperature. So I'm not saying these data are particularly exciting, but I'm showing you the principle of what you do. And I've drawn a little low S line through each one to see what's going on there. And what do we say? Well, these are low, so when solar radiation is low, ozone tends to be low, and there's still not much relationship there, but there's a hint of a positive relationship between, but not a very strong one, between temperature and ozone. When solar radiation is high, and ozone can be higher, but it also depends on wind, because it's higher when the wind is low, but not so high when the wind is high. So explanations get more complicated, but you learn more. And that's what we're trying to do when we're looking at data. We're trying to learn more. So this has got 4 variables sort of related to each other in a way in which we're looking at how ozone depends on temperature for each value of solar radiation and wind. You can get another variable on there if we wanted to have some other variable which was a binary variable in particular, or we can use a different plotting symbol or a different colour. Now, later on in the cars data, which I won't talk about, I do a similar thing with the cars data, but we've got 2 types of car, automatic and manual transmission, and you can plot them with different plotting symbols, and you see that coming out as well. So you can get 5 variables fairly efficiently looking at data in that sort of way. Do I have to stop at some stage? I don't want to outstay my welcome. Have you got? I've got sort of. I sent Sophie some slides. Well, I haven't talked about half the things I was going to. I didn't go. I think I would. But if you want, I think I've time to ask questions, isn't it? Or if you want to ask questions, now's the time.
Do people have questions?
Yes.
Jenny, thanks for the presentation. Why do you like using R?
Well, I started off using S+, and then R was free, so now I use R. I suppose because I like to think, when I started doing statistics and plotting graphs, I had a pencil and paper, and I did it like that. And I could do effectively the same thing using R. I guess it's habit, but I can plot, these are more or less default plots, but I guess I like thinking I'm knowing what I'm doing. That's one thing, in terms of, so when I draw a graph, say for a paper or a publication, I write a program to draw it, and I can repeat that program, I can change it very easily. If the referees want to change, I can change it by changing the program very easily. So I have a program to draw any graph I do for a graph for publication. The other reason I use R, because it's got all the statistical modelling functions in it, of course. I can fit generalised linear models, regression models, distributions, and all the diagnostics, residuals, standardized residuals. So it's got all the built-in, so people, I don't know, what people use here? Do you use MATLAB or something? Yeah. Has it got the statistical models, generalised linear models? Would be the big thing, I'd say. No.
Yeah.
Yeah, maybe it does. I mean, I'm not saying R's the best. I'm just saying I use it because basically historical habit, and also it does the statistical modelling that I understand, that I know what I want to do. So I know. Okay. Yeah.
I have a question on the kernel density estimates. Like, so for the octopodes data, you had a bimodal distribution, and oftentimes you have to do prior distributions. Would you weight those 2 means? How would you?
If you had a prior distribution, is it a prior distribution? Is it expressing your prior opinion of something?
Yes. Yeah.
So you might have a prior distribution that says part of me thinks it's this, and another part of me thinks it's that. And so you could have a bimodal distribution for your prior. You just write down the density function as a formula, which is a mixture. It's P1 times density F1x plus P2 times density F2x, and that would be your mixture of 2 distributions. So that would give you a bimodal distribution. I think you have, in order to get a simple formula, it would probably have to be a mixture. I don't know. Unless you had a very strange formula for a parametric form for a density function that was bimodal. But where do the 2 modes come from? Are they 2 populations mixed together? Men and women, for example, or old and young shrimps. you would have to. But having asked that question, I don't know, have I ever seen anyone have a bimodal prior distribution for anything in practice. So it's original. Yeah.
So usually they use.
Well, usually you have it expresses your idea of what some parameter is before you've seen any data.
New
essentially.
data.
And then you see the data. Suppose you came to me with octopods and said, I'm going to measure some octopods. What do you think their mean? What do you think their distribution would be like? Population distribution. And you wouldn't have. If I was a biologist, I might have a fair idea. They couldn't be more than 5 centimeters long or something. The species. It couldn't be less than 0. So I have a distribution which goes from 0 to 5 centimeters on some scale or other. And I don't know whether I'd do anything. The other thing is you try and get as few parameters as you can. So you wouldn't want to use more than 2 parameters in a prior distribution. A mean and a shape parameter or something. But but that's it's prior. Yeah. People like to use sort of vague priors that don't override the data. Unless you're an economist, you want to override the data because it's not good enough. Or yeah. Yes.
I need a number.
Can you talk a little bit about the when you have the data that doesn't quite obey the parametric test, and then you take the log, of course, et cetera, et cetera. Can you tell me the value of having all the data obeying that, or just the response variable obeying that?
Yes. In principle, if you're looking at some transformation, I mean, one way to get to widen the class of parametric distributions is by using transformations. And log transformations are quite good for that because log normal, I mean, a lot of types of variables measure log normal. Errors that are multiplicative. If you measure something, and when it's larger, its error is also large. It varies more when it's larger. A lot of variables, physical variables, are like that. A lot of biological variables are like that also. So there's a relationship between the standard deviation and the mean, or the error standard deviation and the size of the thing you're measuring. If that increases, so the standard deviation, if the standard deviation is proportional to the mean, or increases linear with the mean, it's what a log normal distribution does, essentially. And so if you take logs, then the standard deviation will be independent of the mean. And that's one of the reasons for taking logs. It also gives you a parametric form, log normal, for that. So when you're looking at, but there are other types of transformation. Rates, for example, rates and times are usually inverse. So if you're measuring a time to some event, and then measuring a number of events per unit time, they're sort of reciprocal. So one's like one over the other, in a sense. And you can do reciprocal transformation. And sometimes it comes out simply in statistical properties, or easy to understand. So that's part of your question. The other part is, do you transform everything? Now I've got an example here in the cars data, where I analysed the logs of both the y variables and the x variables. But that's not necessarily the case. So usually you're looking at the outcome variable, the y variable, as your transformation. But sometimes if you transform an x variable, you turn a curve into a straight line. So it's again, it's the context and whether that works in your problem. Not just for those data, but it works in a sort of logical way as well. One of the problems with log transformations, if you've got something which is 0, you can't take log of 0. Something which can be 0. So when I measure OSL equivalent doses, you can get a 0 dose. You can put a dose in and try and measure it. So you can't take log of that. So there are zeros and also negative numbers. So a lot of transformations are to do with transformations of positive numbers that vary more when they're larger.
Great, it's after 10, so I'm just aware of the time. If anyone has more questions, maybe ask.
You might have real work to do.
Yeah. Thank you very much.
Okay.
I don't know. I guess we need to do that.
They're on.
Are we moving in here?
Just like a chair. What's your meeting like?
The CHP.
It's just 10. Is this one stack? This is a road.
Yeah, it's a road. I think it must have come from. Otherwise.